a hack. That's reminders for my stuff. Don't look at it, you creep. Let me see if this is okay. Yeah. So yeah. Back to what I was saying. I made 3 out of 3, and thank God. You know. I think that a lot of what I do is lucky or God sent, because a lot of times it's really ridiculous how things work out for me. So I think God exists. So yeah, now we have to prove. What were we doing? Okay. Kobe. Okay. That did not work. So now we have to prove that whatever map was surjective. This map is surjective. Is this it? Is it RN? Yeah. So, first of all, I'm gonna get into what a surjection is, because I clearly have no idea what a surjection is. Well, I didn't, because I cannot read. I have severe dyslexia for some reason, and I'm autistic. So, what a surjection is for like any function. Say, I'm just gonna say this function and stuff. So yeah, it means that for every y, for every element in this set, right, you're mapping it to, there exists. This is the symbol for there exists an x in the domain, such that f of x is equal to y. This is the definition of a surjection. So yeah, we're gonna use that for this next one, for our next trick, our next opening act. So okay, so yes, so we're gonna first of all have a function, right? A germ, a germ, right? Function paired with an open set, right? Oh yeah, this is also how you denote germs, right? This is the function, and this is the open set it's working on. So yeah, V is gonna be arbitrarily small, small as we want it. It doesn't fucking, who cares? And it's also going to be an open ball. Right? Or star-shaped. Yeah, you like that? Star-shaped. It's an open ball. Not even an open ball. I think it's just a ball. My ball's on the floor, dog. Let me check. I'm doing the proof right. I cannot do a proof incorrectly because that would be bad. Yeah. It is an open ball. Right? So with this, there's actually another theorem, but I will not go into it. But it really makes sense. That says that then f of x, right, should be equal to f of p. It's a lot like it's like Taylor's theorem, basically. Plus the sum of all xi components, right? Because yeah, minus pi. P is a point, right? So it's a vector technically, times gix, right? Okay. Gix is just a smooth function. God damn it. I'm ruining this book with my dirty marker fingers. So dirty. I want to touch you with them. Okay, I'm sorry. It's like, sometimes I think it's funny, but then when I say it, it's just fucking weird. Okay. So, yeah. These are functions, right? Yeah. G of I of P is going to be equal to So this is what the theorem states, since this is an open ball, right? It makes sense, so trust in the theorem. I'm not going to explain why. So, right, so we take the derivation of this, right, of this function, take the derivation of this function, right? The derivation of f of p is just going to be a constant. What's the derivation of a constant? 0, right? 0, 0 nuts on my sack. Okay. Yeah. So, and then this is also just going to be a constant. So then we have the derivation of the sum of xi, gi of x, right? So, this is just going to be this is going to be the sum of the derivation of xi times gi of x, right? Boom, bam. So now we have a product of two functions. So now we can use the Leibniz rule. Ooh, 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 goo, 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 gaga, goo, goo, gaga, goo, goo, okay. Oh, if I could stop. So this is then going to be equal to the sum of the derivation of xi times g of I of p, right? This is Leibniz rule, I believe. Let me. God damn it! Why did I close this book? I'm an idiot. Let me check. You always gotta be. I always gotta check. I'm doing this correctly. Yeah. G of I of p. Yes. Hold up. Oh fuck! Damn it! Damn it! So fuck. Shit. Balls on the walls. Balls on the walls. Balls on the walls. We got these balls on the walls. Okay, so let's just I also forgot something. Let me just do this. Let me do this real quick though, because this is still technically correct. Sum of p of I, g of ix. So what I forgot is that p of I is sure it's a constant, right? However, we also have the fact that it's attached to g of I of x, right? So I forgot. I'm sorry. I'm a boob. I'm a booby. Boobies. So okay. So it's gonna be now minus p of I, g of I of x. There we go. I'm such a boob. I'm sorry. I'm sorry for being a booby. So we cancel this out. And this is the derivation of f of x. I'm a booby. Okay. I'm autistic. So, yes. So, now this actually shows us that D is nuts. Okay. Yeah. God damn it. Why do I keep closing it? For God's sake. Oh, yeah. Oh, yeah. So we also have the fact that g of I of p is equal to this. The derivative of f with respect to xi at p, right? So this is going to be equal to d of I of x of d of f dxi p. My bad, my boobies. Okay. So, okay, now it makes sense. Okay, so now what this implies, right, is that d of v of f of x is going to be equal to d of f of x for v equaling to d of x1 all the way to d of xn, right? So we could just say that d of just the derivation at v is just equal to a general point derivation, right, for this vector, which means that we can assign we can assign for this function, right? Any x, right? For any x, we can assign for any y, we can assign a phi of x, right? For any output of this function, right? And thus this proves surjectivity. Okay. But this also implies, right? So the entire reasoning for caring that it's an isomorph, well, of course it's cool that it's an isomorphism, but the reason why we particularly care about this is because what this means is that with an isomorphism, right, and in linear algebra, this means we could change our basis, our bases. We could change the basis, right? So we have in a general vector, right? And also, I'm going to tell you, actually, one other thing to note. No, actually, we're not going to do that. Yeah. So for a vector in T of P of Rn, right? V is going to be equal to, okay, shit, my bad, shit balls, Vi, Ei, right? And then for a derivation in D of P Rm, this derivation is going to be equal to sum of Vix P, right? Which then means this basis right here can actually correspond to this basis, right? Using the fact that in isomorphism, right, you can look at this in linear algebra. This book is the best at linear algebra ever. Don't get any other book because it's an engineering book, and for people who think that E is equal to 3 and are fatties. They are fatties if they do not use this book. This book is the best book on earth. Use this book. Kenneth Hoffman, Ray Coons, okay? Don't listen to the other fatties. They're all fat. They're all obese, okay? Obese people do not understand the world. So, okay. So, yeah. Which means that E of I to E of N corresponds to D of X1 P, D of Xn P. And for P is equal to the 0 vector, they're just basically the same. Okay? So, first of all, the isomorphism theorem kind of makes sense already, that it could be true. If you know the isomorphism theorem. First, and I'm going to tell you the intuition now, right? I'm going to give you the little intuition I had for this. If you don't, I mean, honestly, if you do linear algebra, it makes sense, but I don't expect you to do linear algebra here. So, first of all, you could say that they're linearly independent, right? Xi, right? If you take the derivative of xi and stuff of 2, this is just going to be equal to 0. If you take it of 1, though, it's going to be equal to 1, right? So each xi is going to be completely, it doesn't even look at the same thing, right? They're not even looking at the same coordinate axis. It's only looking at the left and right axis for x1, for example, right? If we say so. If we say that's x, that's what x1 represents. Just like E of 1, which is equal to 1 of 0, right? So, in a way, so basically, simple intuition is that they each assign, okay, I'm going to put this here so I don't have to keep on erasing and then redoing it and then being autistic. Okay, so they all each assign, right? They all look at their own coordinate axis, right? And they all assign a specific value. So if you have 2 of xi, x1, this is going to be equal, you take the derivative of this, and this is just going to be equal to 2, right? And if we start off, we're going to get 1, right? A lot like the basis vectors. If you look at, 1, it starts off as 1 and stuff. I mean, obviously, there isn't as much of a geometric intuition to it, but you could definitely see how it makes sense that each of these assign their own coordinate, all right? Secondly, you might be saying, oh, well, so the biggest gap I had in this was that this is a function, and it seems as though these are not. So, okay, goddammit, now I'm gonna have to edit this video. So first of all, I'm gonna tell you that that's stupid, and this could also be a function, if it so pleases. I'm not gonna show you, how so, but I will show you a real example of how it could be a function. Well, anything could be a function, really. I used to think this was just, maybe it is category theory, I don't fucking know. But 3 is a function. And I know this for sure because I've been studying AG, well, I haven't really been studying. I've been really lacking in that department right now. But, in like the first page of this book, it says so. It says, stuff about range. I'm not going to get into that. But anyways, so this is an element of Z, right? And it actually assigns a function from a spectrum of Z 2z. Right? Any element though, really. X is that, right? And the function for 3, like 3 to 5, right? So spectrum of z is going to be like z, but like without a lot of it. So, say we have 3 to 5. This is going to be equal to 3 mod 5, or I don't know which way it goes. Point being, this is a function and stuff. It uses whatever this identity is as 1 plus 1 plus 1 equals 3 and stuff, and then incorporates it with this input and stuff. It may not seem like a function, but it is and stuff. And this is used for generalizing algebraic varieties and affine varieties, right, to affine schemes. Okay, I'm not gonna get. So varieties use functions and stuff, and schemes use rings and stuff. And varieties use ideals, which is a polynomial, and then schemes just use basically scalars and stuff. But they assign it as a function and stuff. Point being, it exists. Point being, too, is that just because this is a function doesn't mean it doesn't have to translate to only a function and stuff. You only see this as a function because you know it is a function. It could be anything else. It could have been a basis vector for all you know and stuff. It's just a mere notation and stuff. So point being, this could also be a function, basically, if you so please and stuff. The difference is you know this as a vector first and then a function later. The difference is you know this is a function first and a vector later, right? A basis vector later. So that's the point I wanted to get out of the way and stuff. And again, like I said, this assigns this one basically, both of them really stuff look at their axis, right? And they assign a value to that axis and stuff. They basically, yeah, they are representative of this axis, right? The horizontal axis in this case, right? And then the same could be gone for every single other one. So, final point I want to make is that vectors, they don't even have to be you don't have to look at them as geometric. The literal definition in this book, okay, of a vector is a set of objects. It's literally just an element in a set, right here. Okay? Hold up. Let me point at it. Right here. Alright? You don't have to fucking... Just because it's... Yeah, you're just a point on a set. That's the definition of it and stuff. So, they're not limited to your own little bracket notation crap. So it's just notation. Anyways, so yeah. I spent a lot of time on that. Yeah. Final point I want to make. Now we get into vector fields, right? Well, actually, just simple vector fields. So a vector field is a function on an open set of Rn mapping to a vector, the tangent space of Rn. A vector field's for Rn, though. And a vector field, so this specific vector could be represented as this, the sum of whatever this is. I'm going to explain what this is, and its basis vectors. This is just an arbitrary function, and yeah, this is a member of Rn, right? This is a smooth function, just basically index notation as to not, like, you know, specifically limit it to a certain number and stuff. Reason why we use a function instead of, like, you know, just a normal scalar and stuff, a function at p and stuff, is because for a vector field, it's just going to be this function, right, and this basis vector without a point and stuff. So this is what we, this is our notation for vector field, and this is the notation for general vector stuff. Alright, so this is our new notation for vector field. So now I'm going to get into as to why we really care about all this stuff in the first place.